We are given this ordinary differential equation, y prime equals 2xy, and we want to look at the existence and uniqueness theorems applied to this ordinary differential equation. So the first thing we want to do is identify the function f, right? So the existence and uniqueness theorem applies to, y prime equals f of x comma y, and you're also given an initial condition, y of x naught, equals y naught. Okay, so our f of x comma y is 2xy, right? That's y prime equals f of x comma y. The first thing is, is f of x comma y discontinuous anywhere? Yes, anywhere. Anywhere. And the answer is no, right? This is a very nice looking function, 2 times x times y. X could be anything. We're not going to get a division by 0. We're not going to get a natural log of 0. We're not going to get an, e to the infinity or something, weird like that. Same thing with y. We can plug in anything for x, anything for y, any point in the xy plane. This will come out with just a number. It's continuous everywhere. All right. Well, what about then, partial f? Partial y. And let's go over how to compute that. So that's the partial derivative with respect to y applied to this function, f of x comma y. Okay, well that's partial y applied to 2xy. Right, so this is really kind of notationally, we're just going to treat this as taking the derivative of some function, in this case 2 times x times y, and we're going to treat x as a constant and take the derivative as if y is the variable we care about. And so if we do that, then the derivative of the partial derivative with respect to y of 2xy, well, 2 is considered a constant, we're going to leave that alone. X is considered a constant, we're going to leave that alone. Y is not a constant, that's the variable we're taking the partial derivative with respect to. And so that y will end up turning into just 1. All right, so, and then we get 2x. No y prime pops out, it's just taking the derivative of y like it's an independent variable. Okay, so we've done that. There's a little example. And now the question is partial f, partial y discontinuous? And the answer is no, right? Everywhere we plug in, y doesn't matter anymore. We can plug in any y we want. It doesn't affect 2x. You plug in any x you want, 2x is going to be, a nice behaved, well-behaved function. So from here, from this no, that meant we had existence, meaning there's at least one solution. And from here, we have uniqueness. Uniqueness. All right, so if we were unable to solve this ordinary differential equation, then given an initial condition, we would at least know that we're going to be able to find a solution that goes through the initial condition, and that solution is going to be unique, and that a solution will exist for some area around the initial condition. You won't run into any strange behavior. It's going to be a well-behaved function. Turns out that we can actually solve this. So this is a separable ordinary differential equation. You can also use integrating factor to do this. There's more than one way. And I'm just going to give you the answer to save time. So the solution is y of x is equal to c e to the x squared. And right, you can kind of see that if you take the derivative, y prime equals, okay, well c stays the same. E to the x squared, that'll stay as is, but right when you take the derivative of e to the x squared, then you multiply by the derivative of the exponent, so x squared prime. So that ends up being c e to the x squared times 2x. All right, well, this thing right here, that's y. And right, so this we could also write as 2 times x times y. And that's exactly the ODE we started with. So yes, this is a valid solution. If you were to plot these out, and I'll try my best here, not the best artist. Given some initial condition, let's do an easy one on the axis. the solutions end up looking something like this. I'll try and draw them symmetrically. Kind of parabola shaped. A little different though. And it kind of continues, so it gets a little, shallower as you get further down. And at the middle, it's a flat, in the x-axis is just a flat line. That's when c equals 0. And then, you start getting, the ones on the negative side. And I actually recommend this tool by Ariel Barton from University of Arkansas. She put it on her website. It's really good at, graphing solutions to differential equations. So yeah, if you go back to my webpage, there's a link to that. And you can actually go there and you can, it's an interactive. You can put in an equation and you can actually, click places, and it'll actually draw the solution for you for that particular initial condition. But yeah, this concludes our first example. So we tested, f of x comma y. It wasn't discontinuous anywhere, so we knew we were going to have an existing solution. We also tested partial f partial y and computed that. That wasn't discontinuous anywhere, so we knew we were going to have a unique solution going through every single initial condition. And it turns out we can solve this particular differential equation. The ones coming up we won't be able to, but the solutions end up looking like these, kind of parabola shaped.